Let's look at the operating structure of each type of DC-DC converter and learn about the selection method of major components and the placement and layout method of components in actual design. The method of converting DC voltage can be classified into linear and switching methods. Linear regulators include the representative 7 to 8 series and LDO with small input-output voltage drop. The linear method requires an input voltage higher than the output voltage, and since the loss is very large when the potential difference between the input and output is large. The switching method was developed. The switching method can obtain an output voltage lower or higher than the input. And high efficiency is possible regardless of the input-output potential difference. A simple comparison of the characteristics of the two methods shows that the linear regulator, which is a simple voltage drop method, has less noise than the switching regulator. And compared to the linear method that can only step down, the switching method has no restrictions on the high and low input and output voltages. In addition, the linear method requires only a capacitor as external components, while the switching method requires additional inductors and switching elements. In terms of efficiency, the switching method can achieve high efficiency of over 80%. DC-DC converters are divided into non-isolated and isolated types depending on the components and method, that is, topology, and the non-isolated type is mostly used. Depending on the method of controlling the switching elements, i.e. the modulation method, it is classified into pulse width modulation, PWM, and pulse frequency modulation, PFM. And a feedback structure is required to obtain a constant output voltage, and it is divided into three methods of feeding back the output voltage, output current, and hysteresis of the output voltage. In the topology of DC-DC converters, it is divided into a non-isolated method in which the input side ground and the output side ground are connected, and an isolated method in which the input side ground and the output side ground are separated. Most DC-DC converters use the non-isolated method, and the isolated method is mainly used in AC-DC converters. There are many different types of non-isolated DC-DC converters. The most basic DC-DC converter structure is the buck converter for lower output voltage than the input, the boost converter for higher output voltage than the input, and the buck boost that outputs a negative voltage relative to the input. There are four types of converters that apply these basic structures. Sepic and Zeta are converters that output a constant plus voltage regardless of whether the input voltage is higher or lower than the output. In general, Sepic and Zeta are mainly applied to the purpose of outputting a fixed voltage by taking as input the output voltage of solar panels or batteries with large output voltage fluctuations. For example, they are used when a fixed voltage of 3.3 volts is required even if the output voltage of a lithium-ion single cell changes from 2 volts to 3.7 volts. Cook and X are converters that output a constant negative voltage regardless of whether the input voltage is higher or lower than the output. Additionally, Sepic and Cook can be combined to form a power circuit that requires the same plus and minus output voltage for a single plus input voltage. And Zeta and X can also be combined to form a plus and minus dual power circuit. In summary, buck is step down, boost is step up, and buck boost is a method of outputting negative voltage, and can output a negative voltage that is absolutely lower or higher than the input voltage. In other words, it can output a voltage of -2 volts to -12 volts with a 5-volt input. Sepic and Cook are paired to produce a positive and negative voltage output of the same size with a positive DC input. And the absolute value of the output voltage can be less than or greater than the input voltage. That is, with a 5-volt input, it is possible to produce an output of plus or minus 3.3 volts or plus or minus 12 volts. Zeta and X can also be configured as a pair to obtain a dual power supply with the same output value. These SEPIC and COOK and Zeta and X require one additional inductor and capacitor each in the basic buck or boost circuit. SEPIC, COOK, Zeta and X will be covered in detail in the DC-DC converter topologies section. If we look at the efficiency of the two methods, PWM and PFM, which are classified by switching control method, the MOSFET used as a switching element in a DC-DC converter has a lot of energy loss during the on-off transition time. The reason is that when the voltage and current changes between the drain and source of the MOSFET overlap during the transition period from off to on or on to off, the power P is voltage times current, so switching loss occurs during the rising and falling time section of the MOSFET. In a section other than this transition period, that is, in the on state, there is almost no loss because the VDS is almost zero, and in the off state, the drain current is zero, so there is no loss. Therefore, the efficiency depends on the switching number of times. Regardless of whether the load current is large or small, the PWM method is disadvantageous in terms of efficiency for light loads because the switching number does not change. While the PFM method has relatively less loss because the frequency is lowered for light loads and the switching number is reduced. That is, when the load current is large, both methods have almost the same efficiency, but for light loads, the PFM method is advantageous. Depending on the DC-DC IC, there is a hybrid method that automatically switches between the two methods depending on the load, thereby increasing efficiency even in the light load range. In DC-DC converters, feedback control has three types: voltage mode, current mode, and hysteresis mode. Similar to linear regulators, DC-DC converters also use feedback loops to regulate for a constant voltage output. Voltage mode is the most basic and common method, which detects the output voltage and performs feedback control. After receiving the output voltage as feedback, it performs voltage control feedback processing, and then drives the driver through the modulation section. The advantage of this method is that it is relatively simple. Using a feedback loop composed of only voltage, has a shorter turn-on time, and has high noise immunity. The disadvantage is that the phase compensation circuit is somewhat complicated. Current mode is a variation of voltage mode control that senses the inductor current for feedback control. Current sensing can also be done using the on resistance of a MOSFET or a current sense resistor instead of the inductor current. Current mode is relatively complex to control because it has two types of feedback loops, a voltage loop and a current loop. However, current mode offers the advantage of a significantly simplified phase-compensated circuit design. Other advantages include a very stable feedback loop and faster load transient response than voltage mode. The disadvantages are low noise tolerance due to the high sensitivity of current sensing, and the circuit is complex. The hysteresis control method was developed to meet the very fast load transient response of load elements such as CPUs and FPGAs. It is also called ripple control because it detects the ripple of the output and performs control. This method provides the advantage of very fast transient response and elimination of the need for phase compensation due to direct control of the comparator. Let's take a look at the main components of a DC-DC converter. Power MOSFETs for DC-DC applications must have short rise and fall times when turned on and off for high-speed switching. Since this high-speed switching is achieved by the internal capacitance of the MOSFET, it is recommended to select a MOSFET with input and output capacitances of less than 1000 picofarads. In addition, a type with low on resistance between the drain and source of the MOSFET must be used to reduce switching loss. It is common to use a Schottky barrier diode with low forward voltage to minimize losses due to forward voltage drop and improve efficiency. And it is important that the diode has low self-capacitance. If the capacitance is high, the switching speed will be slow, which will increase switching losses and increase spike noise when the diode is turned on and off. It is recommended to use a diode with a current rating 2 to 3 times higher than the maximum current of the inductor. The input capacitor should act as a bypass capacitor to reduce the ripple of the DC power supply of the input stage of the DC-DC IC and as a decoupling capacitor to reduce the input stage potential change due to the large current switching of the DC-DC converter. 0.1 microfarad is applied for bypass and 10 microfarad or more is applied for decoupling. For effective bypass and decoupling, it should be placed as close to the IC as possible, and MLCC is generally used. Smoothing load capacitors can be applied to aluminum, tantalum, and ceramic types. In the case of load capacitors, a capacity of approximately 10 microfarads or more should be used. And if a load current of 100 mA or more is required, a capacitor with a larger capacity is recommended. In other words, the larger the load current, the larger the storage capacity should be applied. Aluminum and tantalum electrolytic capacitors have high capacitance and good DC bias characteristics, but they have the disadvantage of large ripple voltage due to relatively high ESR, which causes large self-heating. In particular, aluminum electrolytic capacitors have a serious impact on the product life in high-temperature environments due to self-heating. On the other hand, MLCCs have low ESR characteristics, so they have small ripple voltage and low self-heating. In addition, their size is relatively small, which can reduce circuit space. Since MLCCs can affect performance by decreasing capacitance due to changes in ambient temperature or DC bias effects, an appropriate type of MLCC should be selected considering this. The inductor for DC-DC must be for power use and is determined by the switching frequency, load current, and input-output voltage difference. If possible, it is recommended to use a type with low DC resistance, i.e. DCR. As the inductance increases, the DCR of the inductor increases, which increases the loss and may lower the efficiency. When selecting an inductor, the saturation current, i.e. ISET, is an important parameter to consider at the rated allowable current. If the inductor conduction current exceeds the allowable value, the coil generates heat, which leads to magnetic saturation and reduced efficiency, and increases ripple. Therefore, an inductor with a saturation current, i.e. ISET, greater than the maximum current of the DC-DC must be selected. In general, the type with a smaller inductance value has a larger maximum allowable current, i.e. ISET. When selecting the inductance value, it is selected according to the switching frequency, load current, and input-output voltage according to the relationship. In the relationship, the switching frequency and output current, that is, the load current, are in the denominator, and the input-output potential difference is in the numerator. Therefore, the larger the switching frequency and load current, the smaller the inductance, and the larger the input-output potential difference, the larger the inductance should be. If you look at the inductance value table, the higher the frequency, the smaller the inductance, and the higher the load current, the smaller the inductance. When designing, you can set the inductance value based on the middle load and then tune it according to the load current or input-output voltage conditions. I calculated the inductance values for a buck converter with 12 volts input, 3.3 volts output, 1 amp output current, and a switching frequency of 380 kHz. And a boost converter with 3.3 volts input, 12 volts output, 1 amp output current, and a switching frequency of 380 kHz. Both come out to 21 microhenries. You can get results similar to the values in the table. Ripple current is a transient current that rises and falls superimposed on the DC output current, and is regulated within the range of 20% to 40% of the output current. Therefore, the peak current is the maximum current flowing in the inductor, I peak, which is the sum of half the peak-to-peak value of the ripple current and the DC output current. For example, if the DC output current is 1 ampere, the ripple current is 30% of the DC current, or 0.3 ampere, and therefore the maximum output current I peak is 1.15 ampere. Generally, the ripple rate is applied as 0.3. As the switching frequency increases, the inductance of the inductor and the capacitance of the load capacitor also decrease, which has the advantage of reducing the size of the inductor and capacitor, thus reducing the board size. Let's learn about the component placement and PCB layout of the DC-DC converter. It shows a large current loop according to the on-off of the boost and buck MOSFETs. The components in this loop should be placed adjacent to each other, and the PCB pattern should be thick and short to minimize parasitic inductance on the pattern. According to the voltage relationship by inductance, since the inductance L value is proportional to the current fluctuation, unintended oscillation or ringing may occur due to parasitic inductance by the pattern in a loop where a large current is switched. In a typical PCB pattern, a parasitic inductance of 1 nanohenry is generated per 1 mm. Therefore, in high-power switching PCB layout, the pattern must be thick and short to minimize parasitic inductance. This ringing of large current deteriorates the stability of the entire system and has a very bad effect on EMI, so it is one of the major consideration points in PCB layout. PCB patterns always require corners, but EMI can be worse depending on how the wires are bent. When the wires are bent at a right angle at a corner, as shown on the left, the impedance changes at the corner. This causes the current flow to be impeded, which causes reflections. In high current, high-speed switching loops, reflections due to these impedance discontinuities can worsen the circuit EMI. There are many ways to bend wires, such as using 45 degrees bends and arcs instead of right angles. But the larger the radius of curvature of the bend, the smaller the impedance change. Therefore, the round wire on the far right is the best design pattern. Here are some examples of actual PCB layouts. The first design on the left shows the most appropriate layout. The second design is not ideal because the input capacitor, Cin, is far from the IC, and only the C bypass is placed near the IC terminal. The third design has the input capacitor Cin and C bypass far from the IC, and the freewheel diode is also far from the IC terminal, resulting in a large parasitic inductance due to the pattern. This is the worst design example. As a layout example under the power inductor, the first design is the most suitable layout. An improper layout with an unnecessarily wide pattern like the second one or a design that places a ground layer directly under the inductor is not desirable. It is better to avoid wiring directly under the inductor because the magnetic field lines of the inductor are affected there. And you should also pay attention to the space between the inductor terminals. If the distance between the patterns between the terminals is too close, the high-frequency signal of the switching node can be induced to the output terminal through the stray capacitance. Typically, noise from DC-DC converters and high-speed high-power switching circuits radiates through cables, which act as external radiation antenna paths. To block this potential radiation path, filter circuits are required at each cable connection point. This filtering prevents the H or E fields of the noise source from being coupled into the cable. Therefore, A minimum separation distance is required between the DC-DC converter, which is the noise source, and the connector. Analog circuits and precision circuits also require isolation or shielding measures to reduce the influence of E and H fields. Thank you. Bye.